Hi guys, so now it's time for an example of a Taylor series or a Maclaurin series. We're actually going to start off with the Maclaurin series. So let's take a look. We have a reminder here that if f of x has a power series representation, then the coefficients in that power series can be given by the nth derivative evaluated at c divided by n factorial. So here we're asked to find the Maclaurin series. And remember, a Maclaurin series is a Taylor series whose center is 0. And a Taylor series is a series of the form right up above. And that theorem that gave us that thing right there, that's called Taylor's theorem. So this is the center is 0. So what we want to do here is evaluate the derivatives and plug in 0, and we want to keep evaluating derivatives at 0 until we find a pattern for how those derivatives are behaving. So evaluate derivatives at the center, in this case 0, until you find a pattern. Okay, so in this case, our function is e to the 2x. So I'm going to start off by evaluating f of 0. That gives me e to the 0, which is just 1. Then I'll do, actually I'm going to write this a little bit differently. So we'll have f of x is equal to e to the 2x. So f of 0 is equal to e to the 0, which is equal to 1. Then f prime of x, we have a little chain rule here, giving us 2e to the 2x. So f prime of 0 would be 2e to the 0, and it would be 2. Now f double prime of x, I'm going to remind you here that when we did the derivation of our formula, we said typically we don't want to actually multiply things out. It's going to be easier to find a pattern to understand what these derivatives are doing if we leave everything in its expanded form. More than that, and in this problem it's not really going to be that important, but we're going to keep things based on where they came from. So for example, the 2 in front of that e to the 2x there came from the exponent. I'm about to get another 2 from the exponent, so I'm going to group it with that original 2. So when I do the second derivative, I'm just going to have another chain rule that causes me to multiply by 2 again. So then I'll have f double prime of 0 is equal to 2 times 2 e to the 0, which is just 2 times 2. Now, with this third derivative, we should actually already be able to see what's happening. So when I do my third derivative, I see I'm just going to have another chain rule, and that's going to cause me to pull another 2 down. So I'll have 2 times 2 times 2, e to the 2x. So that means that f triple prime of 0 is 2 times 2 times 2 e to the 0, which is just 2 times 2 times 2. Now notice what's happening. Each time I'm just multiplying by another 2. So if I think about it, that's 2 cubed. That's 2 squared. That's 2 to the 1. That's 2 to the 0. So the pattern that I have found for my nth derivative evaluated at 0, is 2 to the power of n. So that now allows me to go and find my a sub n. My a sub n will be 2 to the power of n divided by n factorial, which tells me then that e to the 2x is equal to the sum, n equals 0 to infinity, of 2 to the n over n factorial times x minus c to the power of n, and that is my final answer for this question. Now, we're actually going to do another example in this video because this one was really straightforward. Things happened really, really easily. And when we have something just like e to the power, oftentimes they will just happen easily. So let's look at one that's actually going to be a little bit more challenging. So next, our example here Okay, so now we're going to find a Taylor series, not a Maclaurin series. We want to find the Taylor series for f of x equals ln x plus 1 centered at c equals 2. And this tells us by first writing the degree 4 Taylor polynomial. So sometimes you'll be told that and sometimes you won't be, but it's useful to know that sometimes, even when you're not asked to find a Taylor polynomial, writing the Taylor polynomial down is going to help you find the pattern. So in this case, it's specifically telling us to, so we have to anyway, and we'll see how maybe that can help us find the pattern. Okay, so same as before, the first thing we want to do is just start writing down derivatives and evaluating them at the center until we come up with a pattern. So my f of x is equal to ln of x plus 1. My center is 2, so f of 2 is equal to ln 3. Now f prime of x is equal to 1 over x plus 1. So f prime of 2 will be equal to 1 over 3. Now f double prime of x is negative 1 over x plus 1 squared. So f double prime of 2 will be negative 1 over, not x plus 1, my bad, over 3 squared. So negative 1 over 3 squared. My third derivative will be negative 1 times negative 2 over x plus 1 cubed, which means f triple prime of 2 will be 1 times 2 over 3 cubed. So notice, even though 1 times 2 is clearly 1, I left that 1 times 2. But I did get rid of the negatives. And that's a good tip, is that if the thing is negative, move one negative to the front. So tips for finding a pattern. Well, we've already said that we want to don't multiply things out, keep them grouped together based on where they came from. So now the second tip that we have here is if it's negative, don't keep a bunch of negatives. Don't have like negative 1 times negative 2 times negative 3. Keep one negative and move it out to the front. And that will help us to see if the thing is alternating or not. And if it is alternating, how is it alternating? If, however, it's not negative, if it's positive, like with the negative 1 times negative 2, don't keep the negatives, get rid of them. Okay, so let's go ahead and take the fourth derivative, and hopefully that fourth derivative will help us to see the pattern that's occurring here. So when I do my fourth derivative, evaluated at x, I'm going to have that 1 times 2, then I'm going to be pulling the negative 3 down, and I'll have x plus 1 to the fourth up here. So that means my third derivative, evaluated at 4, it's negative, so I'm going to take that negative and move it to the front. 1 times 2 times 3 over 3 to the fourth. Well, notice what's happening. If I were to want to write my fifth derivative now, without actually doing any work, I mean my fifth derivative evaluated at 4, without actually doing any work, without actually evaluating the derivative, I can guess that probably it's going to be positive because I'm going to be multiplying the negative 4 down. And so I'll have a 1 times 2 times 3 times 4. And then in the denominator, I'm going to have a 3, and that 3 is going to be to the power of 5. So at this point, we have figured out what our pattern is. So now the question just becomes, how do we write it? So we need to write the degree 4 polynomial because this is what we were asked to do. So our degree 4 Taylor polynomial then, remember, it's just writing out the first 4 terms with their x's. So I'm going to have ln 3 over 0 factorial times, well, nothing, plus 1 over 3 over 1 factorial times x minus 2 plus negative 1 over 3 squared over 2 factorial times x minus 2 cubed. I'm sorry, by cubed I mean squared, plus 1 times 2 over 3 cubed over 3 factorial times x minus 2 cubed plus negative 1 times 2 times 3 over 3 to the 4th over 4 factorial times x minus 2 to the 4th. There we go. That's our 4th degree Taylor polynomial. Now, the first thing I notice is that ln 3 really seems to have nothing to do with the pattern. That's okay. Sometimes when the first few terms have nothing to do with the pattern, we just have to write them out in front of the series. So this is okay. But what that means is that we're going to be starting the series not at n equals to 0, but at n is equal to 1, and then 2, and then 3, and then 4. Okay, so let's look at what the nth derivative will be. So my nth derivative, evaluated at 2, the first thing I notice is when I plug in 1, I want the thing to be positive. When I plug in 2, I want it negative. 3 positive, 4 negative again. So plugging in an even number needs to make this thing negative. So it's alternating, and that means we're going to include that negative 1 to the n plus 1. Now the denominator of this thing is also pretty straightforward. It's 3, well, I have 3 squared, 3 cubed, 3 to the 4th. So that's just 3 to the power of n. Now what's going on the top? 4th derivative, I have a 3 times 2 times 1. Third, 2 times 1. Second, just 1. So we have a factorial there. It's just at 4, I have a 3 factorial. At 3, I have a 2 factorial. So that gives me an n minus 1 factorial. Okay, so what that means then is that my a sub n will be equal to negative 1 to the n plus 1 times n minus 1 factorial over 3 to the n times n factorial, and can be simplified because we have a ratio of factorials. Remember that n factorial is equal to n times n minus 1 factorial. So this gives us negative 1 to the n plus 1, n minus 1 factorial, over 3 to the n times n minus 1 factorial, and those factorials right there cancel out. So a sub n equals negative 1 to the n plus 1 over n 3 to the n, and therefore my Taylor series centered at 2 for ln of x plus 1 will be ln of x plus 1. That ln 3 was on the outside, ln 3 plus the sum, n equals 1. I'm starting at 1 because I left the ln 3 on the outside. Negative 1 to the n plus 1 over n3 to the n times x minus 2 to the power of n, and that is my final answer here. So some things to highlight: we started at 1 and we left the ln 3 on the outside. And we started at 1. Now I'm just going to finish this by rewriting that degree 4 Taylor polynomial because it can look a lot prettier than the way we wrote it. We saw that those factorials cancel out, a lot of things cancel out. This will just be easier to look at if we write it like this. So my 4th degree Taylor polynomial is equal to ln 3 plus 1/3 times x minus 2 minus 1/9 times x minus 2 squared plus 2/27 times x minus 2 cubed, and then minus 6/81 times x minus 2 to the 4th if we actually calculate the values that those things up there would give us. Okay, so you saw that in the first problem, sometimes the pattern's really straightforward. In the second question, sometimes the pattern contains lots of things. We kept the factorial part together, we kept the 3's together, and we saw that sometimes the pattern doesn't fit everything and we have to leave certain things out. Okay, so that's it for this video. I'm gonna make another video where we look at trig functions and see how sometimes the pattern skips things, and we're gonna have to figure out how to deal with that. Okay, that's all. Bye, guys.